All right, so this is the Task 25 video. These first two problems are in the packet pages if you had printed them out, but you don't need to print them out. You can just do this right in your um, notebooks. So we've got a spherical tank. It's got 8-foot radius. The center's 25 feet above the ground. How much work is done in pumping the water up from the ground to fill the tank? So anytime we've got something circular that we're working with, we want the center of that circular thing to be at the origin. So here is our spherical tank. It's got an 8-foot radius. So that's 8, that's -8, that's 8, and that's -8. And the center's 25 feet above the ground. So our ground, I'll draw it green for grass. So our ground here is down at -25. So ground level we're calling -25. So then the center at 0 is 25 feet above the ground. Okay, you always want anything circular, you want the center to be at your origin. So we're filled with water. So from the video before we saw, and this would always be given to you in a question, we have 62.4 pounds per feet cubed is the density of water. Well, we're trying to get a force to put and then times a distance to find out our work in our integral. Pounds is our forced unit for US, meaning we have to multiply by a volume because feet cubed is a volume measurement. The number one thing that people make a mistake on these is what they multiply by the volume of. You multiply by the volume of a slice. I'm going to say it again. You multiply by a volume of a slice. Now we always are going to be pumping up or down, so we always want our slice to be horizontal. It's easier to think about if you draw it in the positive side of the x-axis, but technically it could be done either, but it's easier to think of if you draw it here. So that's our slice of water. So you got to imagine if we have a sphere and we do all those horizontal slices, we need to think about what the shape of each slice would be. Each slice would be a circle with a little bit of thickness. That little bit of thickness right here, when we slice it going this way, is hitting the y-axis. So that little bit of thickness is a dy. So our volume is going to be a circle times a little bit of thickness, which is the dy. Well, a circle is pi times some radius squared, and then dy is what turns it from an area into a volume. And multiplying by that, that'll get rid of our feet cubed and just make it a pounds. So our question now is, what is that radius? Well, in this circle, so this is the top view of our sphere. The radius, remember, only goes halfway across. So our radius in this picture for the circle, remember it's not the sphere because we're working with the volume of a slice. That is our radius there, that red length. Okay, that is what we want to know. Okay, we don't know what that is. And again, this is the radius of the slice, the circle that is in our slice, not the radius of the sphere. So, actually, I'm not going to call that R. Let me take that away. We don't want to call that R. The reason we don't want to call that R is that red line is a horizontal line coming out from the y-axis, and we know we should always call that X. And then what we're going to do is we're going to make a right triangle. This length here is a vertical coming up from the x-axis, that's always y, and then this hypotenuse is the radius of the sphere, which we know is 8. Well, now we can just set up a Pythagorean theorem. We've got x squared plus y squared equals 8 squared, which is 64. And our radius we said was the x, so we need to get x by itself. We'll have x squared equals 64 minus y squared. And when we get x by itself, we'll have 64 minus y squared under a radical. So that is our radius of the slice. So this is now a force because our units is just going to be pounds. We will then have to multiply it by the distance. The distance, we are trying to get the water from the ground and we have to fill the tank. So in other words, we want to think of it as getting to our slice. So that's the distance that our water is traveling when it goes from the ground up some pipe to wherever the slice currently is. So there's our slice right there. Well, part of that, this part right here, is a vertical coming from the x-axis. We know that is called y. Then this part is a set length that we know. That part is 25. So together, our distance is just y plus 25. So now we're going to do our integral, because this is our work here. It's just got to go in the integral. The blue and the red and black was the force times the purple, which was the distance. Any constants can go out front. So we have 62.4 pi. We have our integral. We'll get to the values in a second. Squaring the square root, those wipe out. So we just have 64 minus y squared times y plus 25, and we still got the dy. And then the integral values are where the slices of water can be located. Well, we're filling the tank. So we could have drawn those blue slices in anywhere from -8 to 8. And that gives you your setup for the integral. So we are going to leave for you to do the multiplying out and then doing your antiderivative. But so you can check your answer, that's what your answer should eventually be for the integral. So multiply it out, do your antiderivative, sub in, and see if you can get it to be that answer. All right, so number 3, we've got another spherical tank. The center is 25 feet below the ground now. How much work is done in pumping water out the top of the tank and up to ground level? So we're working with a spherical thing, so we want our center to be at the origin. The center is 25 feet below the ground. So this has got to be 8, 8, -8, and -8. So we want to know where's ground level. Well, ground level would have to be at positive 25 this time, because this is now, the center is 25 feet below the ground. We'll start out with our 62.4 pounds per feet cube. Again, that'll be given to you in a question. If we had this in the packet, it would say it right on top of the page. We need to multiply by the volume, and I want you to think to yourself, what do we need to multiply by the volume of? Hopefully in your head you said the volume of a slice. Okay, you need to get that down for these problems. It's the volume of a slice that you multiply by, because the integral is then going to add up all of those slices. So we'll draw on our slice here. That is going to be a circle with a little bit of thickness. So we're going to have, just like before, pi times some radius squared dy. Everything's going to be the same essentially with our Pythagorean theorem as last time. That's the x, that's the y, this is 8. So we're going to jump ahead and make that the 64 minus y squared again. Now our distance that we have to travel, we're trying to take this slice of water up to the top. So here's where this is going to change. That is not attached to the axis. So let's imagine it is. Let's put in a squiggly. Together, those are 25. But we want to take away the squiggly. The squiggly is a vertical attached to the x-axis. That's always known as y. So we want to take away y from our 25. So now we'll just do our integral. We can put the constants out front. So 62.4 pi. We've got 64 minus y squared 25 minus y dy. And our integral values, remember, are where the slices of water would be. Well, the places I could have drawn those slices are in the sphere from -8 to 8. So this is the answer you should get after you do your workout. Again, we're going to leave that work for you to do on your own and show that it's the same. Um, and notice it's the exact same answer as we just got on the last one. And the reason for that is, notice in both cases, the water was being sent up. Here we already had a full tank and we were pumping it up to the ground. Here it was at the ground and then we were filling the tank. So the distances needed to travel for like the bottom in this one would all be the same as the distances needed to travel for the top in the third one in question 3 and vice versa. So that's why they ended up being the same. So our next question we're going to look at is from the study guide. There's a PDF of it listed right under the task on Schoology. You can either print that out, or if you want to just follow along on here and do it on a separate sheet, you can do that as well. Our next couple of tasks are going to be doing problems from the study guide. So we've got a cylindrical tank. The radius is 5 of the cylinder, 20 feet length, and filled with oil. Notice the density is different here, and we're going to pump the oil out through a hole in the top. So because the cylinder is on its side, that means we're looking at a circle, so we want that circle to be centered at the origin. And basically, I'll do my best to draw like a three-dimensional drawing, but that's then like our cylinder laying on its side. So the radius of this circle is 5. This long way is 20. And we always start with our densities. Let's start with the 40 pounds per feet cubed. In this axis, this is -5. Here would be 5, 5, and -5 based on the radius of the cylinder. We want to get rid of the feet cubed, so we're left with just pounds, which is a force. To multiply by feet cubed, that's multiplying by a volume. In your head, tell yourself, what are we multiplying by a volume of? Hopefully you said we are multiplying by the volume of a slice. So we're going to slice horizontal again because we're pumping everything up. So when slicing horizontally, then all of the oil in that slice will move the same distance. This time when we slice it, a slice horizontal will look something like that. So it's actually a rectangle with a little bit of thickness. Well, a rectangle is the length times the width, and then our little bit of thickness, it slices the y-axis, so it's a dy. So once we multiply by that, we won't have the feet cubed that we're dividing by anymore, it'll just be a pounds. Well, one of the dimensions of the rectangle is always 20. So that stays the same. We are going to set up our triangle again like we did in the other ones. But what we need to keep in mind is we're going to need, if that's x and that's y and that's 5, for our dimension in the rectangle, we actually need 2x. Before, we just needed a radius, so it went halfway across. But this length in the rectangle is all the way across, really. So we're going to need to put in here whatever 2x is. So if we do our Pythagorean theorem, x squared plus y squared is 25. We'll get y squared. Oops, sorry, we want x squared. X squared equals 25 minus y squared. And x is equal to radical 25 minus y squared. So we want this to be 2 times x, so we'll have 2 and then radical 25 minus y squared. So this now is a force. We need to multiply by the distance. The distance is what it takes to go from the slice out the top. That's a vertical line not attached to the axis. Let's put in our squiggly to attach it to the axis. Together, those are 5. We want to get rid of the vertical squiggly, which is just a y. So 5 minus y is what we would have for the distance. So we've got to still set that up in the integral. So our constants can go out front. 2 times 20 is 40. 40 times 40 is 1600. We'll come back to the integral values. We've got radical 25 minus y squared. We've got 5 minus y dy. And where could our slices be? Well, we could have drawn these horizontal slices anywhere from -5 to 5 because it was completely filled with oil. And this is 0 here, by the way. It kind of looked like an 8. And that's it, because they want us to do in this one was just set it up. The reason they're having us just set it up is we can't handle this integral. We can't like FOIL this out or anything when you got the square root. So this is the best we could do other than doing like a calculator approximation of it. So this represents the work it would take to pump all the oil out at the top. So what you have to do to finish this task is you have to go back to the other two questions, 2 and 3. You need to multiply it out, sub in all your things, and check to show that you get those answers that we talked about. Upload your work to Schoology so I can see that you did that part.